Hello everyone. So today we are going to do a case study of pedestrian wind comfort assessment using CFD and OpenFOAM. So you can consider this case as a follow-up to my previous simulation where we talked about atmospheric boundary layer flow modeling in OpenFOAM. So the setup that we are going to do is similar. However, in contrast to the single building case, we have a city block as our geometry, and we will be assessing how the airflow happens at the pedestrian level, and we will post-processing the non-dimensionless velocity ratio to monitor the pedestrian wind comfort. So that's briefly what we are going to do, and also in the simulation we will briefly talk about couple of concepts that are relevant to the simulation, like Reynolds number independence and the concept of similarity, which is required when we want to do reduced scale flow modeling. So let us start, and as we do the simulation we can talk about the different aspects of it in detail. Okay, so once again let's take a look at the geometry. For our simulation we are going to study this particular region of the city block, and we will be using a scale factor of 1000. So the entire geometry will be scaled down in the CAD file by a factor of 1000. And the other thing is the nature of the surrounding area. So our particular city block lies in an urban space, and this information is important for us, especially when we set the wall functions and set the aerodynamic roughness length. We will be using a corresponding value suitable for the urban landscape. Okay, so I have positioned the city block such a way that this road here aligns with the positive x-axis of my domain, and the building height will be in the y-axis. And most of the buildings, they are 4-story buildings, and they have a height of average 12 meters. So I have followed that, and you have this tallest building here which is around 60 meters. But the geometry is mostly approximated for the sake of the simulation. And again, you have so many features on the rooftop, but I have just considered the chamfer and neglected all the details. And also I think that's reasonable, because what we are focusing on is the pedestrian level wind flow, which is at 1.75 meters, and so I think it's a reasonable approximation to neglect those specific details on the rooftop. Okay, so that said, using the trace of the elevation of the city block, I have created the geometry in FreeCAD and scaled down using the factor of 1000. So once you have this, just export it as STL file and save it within the train surface folder of constant subfolder in your case folder. So like I said, I'm following the same setup as in my previous video, but only the input to the setups are differed in this specific simulation. And apart from this, we need to set the direction of flow. When you do pedestrian wind comfort studies, there exists a couple of best practice guidelines, and according to one of them, you need to evaluate the flow for different incoming flow directions. In my case, I'm just considering a single situation, and I found this website where you can get the weather, including the velocity and the direction of flow. And right now, as you can see, the direction of flow aligns with the street parallel to the city block. So this is the same orientation as this one, and the speed of 19 km per hour translates to almost 6 meter per second of velocity. So I'll be using these values in the inlet condition. Okay, so this is the geometry. Now we want to take a look at a couple of concepts that we need to be aware of before we proceed with the simulation setup. So the first concept that we want to look into is regarding Reynolds independence and its significance when it comes to scaled model experiment. In order to have resemblance between the flow over a real scale prototype and over a reduced scale model, you basically need to have three types of similarity: geometric, kinematic, and dynamic similarity. So by geometric similarity, we need to have similar length ratios. So for example, all the dimensions, the buildings, all the distance between buildings, the streets, everything has to be scaled by a common factor. In our case, we have used a scaling factor of 1 by 1000. So by having that common factor, we have geometric similarity. And the second is kinematic similarity. So by that we mean we need to have similar structure for the velocity field. All the flow patterns and the location of the recirculation zones, the streamlines, everything should be similar. Even if the magnitude of the local velocity might be different, the pattern should be same. So you can compare by two velocity profiles perhaps. And for example, in our case we will be working with the velocity function or the wall function, and these wall functions should have a similar shape between the prototype flow and the model flow. Okay, so by having these profiles similar in shape, we basically have kinematic similarity. Okay, so that's the second thing. And the third, which is the dynamic similarity, which enforces that the force ratios between both the flows are similar. So for example, we can monitor that by comparing the Reynolds number in flow or prototype and one in model. So Reynolds number basically is the ratio of inertial force to viscous force, and also if you compare force coefficients like drag coefficient or lift coefficient, then these values should be same in both for the prototype and the model. So these are the three similarity requirements. But the tricky part when it comes to the type of flows that we are dealing, like environmental flows or urban aerodynamics, the geometry is often of large scale. In our case, we have the city block area around 1 square kilometer, and you can't really do practical experiments with such a big geometry. So we obviously need to scale down things, and when you scale down, in order to have dynamic similarity, then you need to proportionally scale up the velocity. If you consider the Reynolds number, when the geometry is scaled down by a factor of 1000, then your velocity should be scaled up by a factor of 1000. So in our case, instead of 6 meter per second, we might have to use 6000 meter per second in the wind tunnel. So that's not practically possible. So this concept allows us to overcome that. So what exactly are we talking? So through various studies, it is observed that beyond a critical Reynolds number, by just having geometric similarity, you can have similarity between both flow over the prototype and flow over the model. So beyond this critical Reynolds number, you don't have to force yourself to match between Reynolds number or have kinematic or dynamic similarity, but instead that will be inherently existing in the flow. So in this particular article, so they have investigated this, and they have tried to address how or what the mechanism is behind this phenomena. They have been able to identify some peculiar things about this phenomena. This Reynolds independence is case dependent, and also within each case or within each flow domain, the critical Reynolds number can vary from region to region. So they have come up with a factor or non-dimensional quantity to identify different critical Reynolds number for different regions, or whether the flow is Reynolds independent in a particular region of the domain. So you can read about this in detail in this article, but in short, they have found a critical Reynolds number range between 60,000 to 140,000. When we do our estimation of Reynolds number in our case for 6 meter per second and a building height of 12 meters, Reynolds number is of the order of millions, and that's well above the limits discussed in the article. So we are in the Reynolds independence zone, so we only have to meet geometric similarity, and dynamic similarity will be achieved inherently. And also to speak about achieving kinematic similarity, so if you look at the wall functions, so which basically defines the physics, if you non-dimensionalize this, basically divide the u set by the friction velocity, then you basically end up with 1 by kappa ln z plus z0 over z0. So here this velocity profile only depends on the z over z0 ratio. So by having the geometric similarity, we are scaling z by a factor of 1000 and also z0 by a factor of 1000. So that's one thing to remember when we set the boundary condition. Whatever aerodynamic roughness length that we are choosing, we should scale that with the same factor in order to have kinematic similarity. Okay, so scale the geometry with a constant factor, and also scale the aerodynamic roughness length with that same factor. Then you will end up with kinematic similarity, and with Reynolds independence you don't have to worry about dynamic similarity. So this is what allows us to have such model scale experiments in wind tunnel. And the second thing is to follow the best practice guidelines for pedestrian wind comfort studies, and this is an article which discusses that. So basically you have dimensional requirements for the domain and also atmospheric boundary layer modeling, things that we have already covered in a previous video. So in short, we have two main things to worry about. With the mesh, we need to satisfy the y plus requirement for the wall function, and also specific to pedestrian wind comfort studies, you need to have at least 5 cells over the pedestrian level, so that's 1.75 meters. So that's two things, and again you can read further in this article. They have explained the workflows, what are the best practice guidelines with the help of a case study and so on. Okay, so that's the two articles that I wanted to mention and the topics that I wanted to discuss about. Now we can see how to set up the domain and also calculate the grading using our hand calculations from before. Okay, so there is one thing that I want to clarify before we look the hand calculations. So I had this confusion in the beginning between the unit system in FreeCAD and when you export the geometry as STL in and open it in OpenFOAM. So the thing is, in FreeCAD I had modeled this file with a default millimeter kilogram second unit system. Okay, so this is the status bar here. It basically shows what unit system are we following, and perhaps you could, before starting the modeling, edit the preferences here and modify it to meter kilogram system, but this applies to new file. Okay, but I had modeled this with millimeter system, so all the dimensions here is in millimeter. Even though it reads 86 micrometer, it's actually 0.86 millimeters. Okay, and similarly most of the building thickness, even though it says 14 micrometer, it's basically the actual dimension is modeled in 0.14 millimeter. Okay, that's one thing. The actual real scale prototype, everything is in meters, and then we want to apply the scaling factor of 1/1000. So in the CFD model we need to have everything in millimeters. There is this confusion. So when you export as an STL file, the thing with STL file is that it basically doesn't store units. So if you have modeled the geometry in millimeters, and if some particular dimension, like maybe this dimension, so if it is in 0.11 millimeter, then in the STL, when you open STL file, perhaps in OpenFOAM or ParaView, you only get the information of 0.11. So we don't know if it's millimeter or meter. By default, OpenFOAM considers all the numerics to be in SI units, so it would interpret things as in meters. Okay. If you want to have millimeters in OpenFOAM, then in the STL file you need to have the right magnitude. Instead of modeling it as 14 millimeters, you need to model it in FreeCAD as 0.14 millimeters. When you export it as an STL file, the OpenFOAM will read it as 0.014 meters. Okay, so that's the logic. It's a bit tricky, but the key idea is that STL doesn't store units. So in order to match the scaling factor, you have to scale the geometry pre-hand and open it in OpenFOAM. So that's something that I want to clarify first of all. So now we can look into the hand calculations. In contrast to the single building case that we discussed, in our city block we have too many buildings. So in order to input into the hand calculations, we need some reference dimensions for an imaginary building. Okay, so I have done that like this. So basically you select the smallest building dimension at the base of the building in each direction. So in my case, I have considered basically this particular scenario. In z-axis 0.14 mm, and in x-axis you have 0.14 mm. Okay, and in y-axis I have considered the height of the tallest building, which is 0.06 m. Okay, and using the building height we follow the best practice guidelines. Keep 5h length in the upstream, at least 10h in the downstream. And one more thing, so if you look the estimation of the width of the domain, you can see that 0.2 length in the upstream direction and 0.42 is the length in the downstream direction. So that the distance from origin to the farthest point in the negative x direction and distance to the origin to the farthest point in the downstream direction. Okay, so you basically have to place the domain boundaries away from the farthest point of the geometry. So that's the basic idea. So based on that you estimate the overall domain dimensions. So this is required for us to define the different coordinates of the rectangular domain in the blockMesh dig file. Then the other important parameter that we want to choose is the aerodynamic roughness length. We saw that the city block remains within an urban landscape. For an moderately dense urban space, you can consider aerodynamic roughness length around 1 meter. So the important consideration here is that in order to have kinematic similarity between the wall function, we have to scale this aerodynamic roughness length with the same ratio as we scale the geometry. So that's what I have done here. So the Z0 model is something that we use in the CFD wall functions, and that's actually scaled using the same factor of 1/1000. Okay, based on that you calculate the friction velocity. Also, when you calculate the friction velocity, you again have to scale the reference height where you measure the rough velocity. So that's 10 times 1/1000. Okay, then using the friction velocity you can reverse calculate the first cell height for a target y plus. So we did that. I chose target y plus as 100 and you reverse calculate the first cell height, and based on the minimum dimension of the building, which is in my case 0.014 meter, you basically estimate a base cell count. Okay, we talked about this previous video. Then we calculate the actual number of cells that we require in the y-axis in order to satisfy the y plus requirement and also a target per selection ratio. So that's the growth ratio between adjacent cells. So I have chosen it as 1.1, and by definition of grading, which is final cell height to initial cell height, we can calculate the grading as r to the power n y minus 1. And so this is the final cell count and the grading that we will be using. So we will have uniform grading in x and z direction and 11.918 grading in y direction. So that are the essential hand calculations that we need to do. So now let's look the blockMesh dict file. So let's open a Linux terminal, then navigate to your case folder. In my case I have defined a case folder named camless.start. Then if you do an ls, you can see the standard, boundary condition, mesh and solver settings files folders. Then the first thing, we can create a FOAM file so that you can identify the folder as an OpenFOAM file folder. So the next thing is to define the background mesh. For that, go to the systems folder, then edit the blockMesh dict file. Okay, and the first thing is the vertices. So if you remember our hand calculations, the background mesh had dimensions of 1.82 in x-axis, 0.36 in y-axis and 1.28 in the span-wise direction. So accordingly I have 0.5 in the negative x direction, 1.32 in the positive x direction, 0.3x in the y-axis and 0.58 in both span-wise directions. So that defines coordinates. Then you define the block and also the number of cells in each direction that we have estimated, and also the grading that we have calculated in y direction. So in x and z direction you have uniform grading, and then you have the domain boundaries. As usual, we have the inlet, outlet defined as patch, ground defined as wall, and top and side boundaries defined as symmetry plane. Okay, so that defines the background or the blockMesh dict file. So save it, Ctrl O, enter and Ctrl X. We are back to the systems folder. Now we can actually create the blockMesh. So go back to the case folder first, then type in blockMesh. So that generate the background mesh. So it's done. Now go open ParaView and navigate to your case folder, then open the FOAM file that we created, and if you apply, you can see the domain. Yeah, enable surface with edges. Then you can see the grading that we have defined y-axis and also uniform grading in x and z direction. So at the moment we don't have the buildings or the city block inserted. So the next step that we want to do is to define the physics. So basically define the boundary condition. And in pedestrian wind comfort studies or atmospheric boundary layer flow simulation, the first step is to check the compatibility of the boundary conditions that we have set. So when you run the simulation, we need to have horizontal homogeneity and the traits of the stable atmospheric boundary layer established before having the buildings inserted. So the background flow should be according to that. So to check that, now we can set up the boundary conditions and run the simulation without having the buildings in. So let's do that. First of all, navigate to the boundary conditions folder. Then if you do ls, you can see the standard file, edit the velocity text file. So here from the previous velocity boundary conditions file, I have changed the reference velocity to be 6 meter per second and also the reference height to be the reduced scale reference height, which is 10 times 1 by 1000, so 0.01 meters. And you have the reduced scale aerodynamic roughness length, which is 1 meter times 1 by 1000, so that's 0.001 meter or 1 millimeter. Okay, so that's the only change that I have made. Apart from that, you have outlet a zero gradient condition, ground to be no slip, all the standard velocity boundary. Just modify the inlet log profile parameter. Control O and Control X. Now we can do the same modification in turbulence properties. First of all, epsilon, and again in the inlet profile modify the aerodynamic roughness length and reference velocity. Okay, and also in the previous simulation we had used two different aerodynamic roughness length, one for inlet and one different one for ground, but in this simulation we are actually using the same. So theoretically speaking, both the ground roughness properties and the roughness properties of the inlet wall function should be matched. Often at times in CFD, because of the numerical attributes, it is at times hard to get this horizontal homogeneity, and often at times we have to tune a bit in the inlet profile. So that's why in the previous simulation, when we tried to replicate the simulation, we had a different value at the inlet and a different value at the ground, but ideally it should be the same. So I'm considering that ideal situation and considering same roughness property for inlet as well as the ground. And also you can, in a more realistic way, if you consider, we talked about the city block lying inside the urban space. So in reality you have different types of patches in the ground. Maybe a region with pavements, maybe a region with asphalt, maybe some region with grass. So at these regions you will have different types of aerodynamic roughness. We are not considering that. We are assuming that the average roughness is uniform. Okay, so that's one assumption that we have, and that's reasonable to have in a moderately dense area. And also the thing I mentioned this is because the incident profile can necessarily have a different roughness length or roughness properties depending on the incoming flow region or the upstream region. Okay, it depends on the application and the surroundings of the region of interest. So in our case we are using the same value for both inlet and ground boundary. Okay, and apart from that we have the similar smooth wall function. So save it, Control O, enter, Control X. Do the same modification in turbulent kinetic energy file. I have modified the inlet profile, then everything else as before, Control O, enter, Control X. Then you have the turbulent viscosity, modify the aerodynamic roughness length for the ground here. Okay, and also like, then you have the pressure file same as before. Okay, so we have the boundary condition defined according to our similarity and everything. Then now we can actually run the simulation. So first of all, maybe I can also show you solver settings. So go back to the case folder, navigate to the systems folder and check the control dict file, and I have kept the end time as 1000. So the case basically straightforward. You don't have to worry about a lot of things without the buildings inserted. Now we can actually run the simulation without the buildings and check how horizontal homogeneity exists. Okay, let's run the simulation by tapping in simple form. Okay, so let's wait a bit for convergence. Okay, so the solution is converged after almost 1500 iterations. I had to modify the end time in between. So let's check the output field, reload the file. I have also inserted the STL file of the city block in order for us to have a reference. So in the simulation or in the mesh, we haven't considered the city block yet, but to check the fields, I have added this. Okay, and we can have a slice in the set normal, apply, hide the plane, and we avoid the triangulation. Okay, also select the converge iteration. Okay, and if you look the velocity field, it's perfectly fine. Then you have epsilon, we have horizontal homogeneity, so you can see a small gradient here, but that's okay. What we are concerned is mostly the upstream part of the city block and also in the vicinity of the city block. This is totally fine. Okay, and if you check the turbulent kinetic energy plot, again this region here looks horizontally homogeneous, and if you check the values here, or if you probe at some level, it says 3.5, here it's 3.5, here it's 3.5. so again we have horizontally homogeneous field. So this is good. We can proceed to rerun the simulation with the buildings inserted. So, and in the turbulent kinetic energy plot, again you have a streamwise gradient present in the top right corner, but again what we are concerned is mostly this region where the incident profiles are most important to us. Okay, so this is fine. So we don't have to have a horizontal homogeneity in the entire domain, but we need to have it very near the building. Okay, so this is fine. So now let's edit the snappy mesh file. So before snapping, we want to do the surface feature extraction step. In contrast to the single building case, we have a relatively complicated geometry with lot of feature edges, especially this chamfer. So I want to resolve this sufficiently with this too many elements in the geometry. It's better to use the feature extraction step. Okay, and we have to do that before setting up the entire snappy hex mesh dict file. Okay, so for that, in the systems folder, if you do an ls, you can see the surface feature extract dict. So if you don't have a file like that, just create a text file, and if I open it, surface feature extract dict, so this is how it looks like, and inside you basically have the geometry file and also extraction method extract surface, and you have this parameter of included angle. So this is basically a pre-step to meshing, and when you do the snapping operation, the mesh has to adjust itself to match the STL surface, and having this surface feature extraction helps the snapping algorithm to identify the edges rather than search for it. Okay, so this included angle is basically the angle between the surface normals of adjacent faces. So if you have the normal angle greater than this included angle, then you basically identify that shaded as a feature. That's the idea. Okay, so let's save it, and once you created that file, go back to the case folder, do the command for feature extract. Okay, so this basically create a number of obj file and also this emesh file, so that basically stores the information about the edges, and we will use this emesh file within the snappy hex mesh dict file. Okay, so now we can edit that. So go back to systems folder and edit the snappy hex mesh file. Okay, as before we are not using layers, so I have disabled that. Then you add the geometry STL file, then you define the volume refinement zones that you want to have. So if you remember, we have two requirements with the mesh. First, we have to meet the y plus requirement for wall function. The second one was that we need to have at least 5 cells within the pedestrian level. In order to achieve that, I have iterated volume refinement. So one is basically a wake refinement, which again starts a bit upstream of the building. Then you have this box ped zone, which is basically add additional refinement very close to the pedestrian height. Okay, and once we do the meshing, I can explain how that works. Okay, so if you remember, the pedestrian height is 1.75 meters, so it will be 0.0175. Okay, and within that height you need to have at least 5. Okay, so this is where I define the zone, and then you basically define the surface refinement level. So here I have used the minimum and max level as 3 and 3. If you set it as 3 and 4, then the surface refinement can be adaptive to have a higher refinement near the corners or edges, but in my case I'm using uniform refinement, and I feel that's more robust, I guess. Then you have the refinement level specified. In the wake I have level 1, and in the pedestrian box I have level 3. Okay, then here is where you mention the eMesh file that we just created, so that basically help in meshing. Then you have this resolve feature angle, so that's basically, so these angle and the included angle, they happen in 2 stages. So the included angle that we saw earlier is something that is used in the surface feature extraction step, and this is some angle that is used in the meshing stage. So it basically helps identify edges during meshing, and if you have basically a level 3 and 4 in surface refinement, so based on this resolve feature angle, it identifies the edges and applies additional refinement like level 4 near the edges and level 3 in other part of the surface. So it uses in multiple ways in the meshing step. And you have again a feature angle within the snap control, so that acts like a limiting angle to the snapping step. Okay, since we have a chamfer to resolve partially, I have used the number of smooth patches to be 3. So if you keep it as 0, then it will be a very blocky thing. If we have cornered objects like the previous single building, we can keep it 0, otherwise you need to have a finite number here. Then you have the tolerance, which is the distance that you allow the snapping to move. Then you have the solver iteration, which controls the iterative cycle of snapping, and this is the damping for that iteration. Okay, and here I have some additional thing which basically tells the snapping algorithm to stick to the parameters. Okay, so then in the default mesh controls, I have just modified the maximum skewness to 15. So again, in the mesh settings, I have iterated and I found a suitable mesh. I'm just showing the final mesh settings that I am using. I'm not using the add layer. Okay, so the key things are to mention the eMesh file and also to have the volume refinement in the pedestrian level. So having done that, save it, go back to the case folder, and now we can actually do the snapping operation. Okay, I had cleared all the mesh before, so I will create a block background mesh once again. Yeah, and now type in override. Okay, so if you already had the blockMesh file, then you just type in this, because since I had cleared all the mesh files before, so I did the blockMesh first. So you might don't have to do that. Create the snapping operation, and it's going to take some time, so let's wait. Okay, so it took a while and we have the final snapping done. So in the final snapped mesh, you have almost 3 million cells. Now before we check the mesh, we can do a sanity check by checking the mesh quality. Type in check mesh. Okay, so you have the final confirmation that all the mesh quality is sufficiently fine and it's okay to proceed. So before that, we can visualize the final mesh. Just reload the FOAM file, and also I have removed all the previous results from our simulation without the building. Okay, so this is the final mesh, and you have the refinement zones inside, snapping done. Maybe I can hide the STL file. So this is the final snapped mesh. You have all the buildings, especially the lateral surface that concerns us the most, sufficiently refined. You have to iterate a bit on the snapping settings in order to have a final okay mesh. Okay, so this looks fine to me. What I'm concerned most is this lateral surfaces of the building rather than the chamfer at the roof. Okay, however, even if you have some cells failing at the roof chamfer, that will also affect the result. So if you have an okay for the mesh, then it's fine. So if we again observe the slice, the warning, it's okay. And if we check the slice, you can basically see that we have the wake refinement over the building, and then you have this refinement very near the pedestrian level. And if you probe the coordinate 1, 2, 3, 4, 5 above the 5, you can see that 0.00185, which is almost 1.85 meters or close to 1.75 meters. I think this is fine. Maybe you can have a bit more refinement so that it satisfies perfectly. but having a small jump in refinement at this stage will explode the number of cells, and it's already 3 million, so I think it's okay for the time being. So this is our final mesh, and now we can set some post-processing functions and then rerun the simulation. Okay, so let's look that inside the system folder, check the solver settings and overall date. So here I have specified the end time as 2000. Then you have the standard functions as before, the y plus. I have the expression for CPS before, and have the velocity probes to monitor convergence, and additional to that I have added a expression which evaluates velocity ratio. So that's basically a non-dimensional parameter. So it's the ratio of local velocity, this magnitude of local velocity, to the reference velocity measured at the meteorological reference height, which was 6 meters. Okay, so when you do reduced scale experiments, you compare between the actual flow and the reduced model scale flow with the help of non-dimensional parameter. And in the reference article of Pedestrian Wind Comfort Study, they have demonstrated using non-dimensional velocity ratio values to study the pedestrian wind flow. Okay, so I have used this used the same. Okay, so again, so the key idea, you need to have something to post process. So you basically add the functions here and also set the solver time, and instead of latest time, modify start time, since we are rerunning the simulation. Okay, so Control O and Control X. Then again we are using the same turbulence model as realizable K epsilon, and everything is the same, present in the constants folder, CD 10, and inside turbulence properties you have the type of simulation and the turbulence model specified. Okay, so that's the same as before. So now we have everything set up. Now we can run the simulation, and it's going to take a while since we have, it's relatively a big problem with 30 million cells. So let's run the simple form, and also in a separate terminal we can open the velocity probe CD. Okay, so type in this command, so tail, which tells that you have to print the final entry of the text file, -f, which means you have to follow the updation in the file, print every latest version of the file. Then you specify the path in the case folder, then you specify the probe that you want to print. Okay, and all of, okay, so then if you type enter, you can see the probe. So let's monitor that and see the result. Okay, so it took couple of hours for the solution to converge, and it converged after 800 iterations, and also in the velocity probes you can see that the velocity is converged very well. So the first probe is in the upstream part, and the second one is in the top of the city block, and the third one is probed at a downstream location. So everything is converged. So let's go to the paraview and reload the form file. Okay, so the result is loaded. What we want to check is the velocity ratio. So you have this velocity ratio here. Okay, and also what we are interested is velocity ratio at the pedestrian level. So let's create a slide of it. Select the domain and then create a slide, this time as y normal. Okay, position it with the y coordinate at the pedestrian level. So that's 0.00175. Okay, I hide the plane, triangulate, apply. Yeah, so that at the pedestrian level I can hide this slide, and if we check the velocity profile, so this is how it looks. Yeah, so in pedestrian wind comfort studies, our objective is to evaluate how the free stream flow gets altered when it enters different streets, to identify accelerating regions as well as stagnation regions or recirculation regions. So we have created the velocity ratio function. So that means the local velocity divided by the reference velocity. So the reference wind speed is 6 meters per second. So if the velocity ratio is greater than 1, means that the velocity or the local flow is accelerating in that region. And if it's less than 1, then it's decelerating in that region. Okay, so that's how we evaluate things. If I clip the maximum to 1, minimum to, yeah, minimum can be the same value, then you can see that all the red spots are regions where the flow is getting accelerated. Okay, you have different effect here. So here you can see a kind of a Venturi effect where the flow is kind of squeezed in between the buildings. So here you have a high acceleration, and also there is this flow separation here, and you have a recirculating region. So here the velocity ratio is around 0.2 or 0.3. That indicates a recirculation zone. So the pollution dispersion properties will be very poor here. So if there is dust particle would accumulate over there. Also you have wind accelerating as it approaches every corner. So that's some behavior we see in pedestrian wind flow. Have again a Venturi kind of effect here. So the flow is kind of jetting through the street. Okay, and maybe I will rescale it. Yeah, so that's how you interpret this data. So based on, so what we want to do next is to mitigate this accelerating region based on the comfort criteria. So you have different comfort criteria available. So there is one Lawson comfort criteria which says that if a person is walking, then the comfortable wind speed is around 6 to 8 meter per second. So that's one point. So if it goes beyond 8 meter per second, then things become uncomfortable. So that's one thing. And maybe we can also see the vertical slice at front location. So if we enable it, then if we try to see it different location, you can see how the wind flow is altered to plane. Yeah, so this is how it looks. And if you check the turbulent kinetic energy, you can see that the buildings are causing a lot of turbulence near the vicinity of the city block. And now we can create some streamlines and see how the flow is actually moving through the city block. So just select the form file, and then you can find here streamlines in a vector field. So vectors velocity, then maximum streamline length, let it be like that, seed type line. So we get the streamline passing through all the seed points. Okay, I will choose x can be minus 0.5, 0.2 can be minus 0.5 itself, then y can be at the pedestrian level 0.00175, and z can be that value. Apply. Okay, so these are the streamline. So you can see also different patterns happening to the flow. Here you can see that the airflow is getting pushed upward by this recirculating region, and then it creates large scale structures here in the wake. Okay, and here you can see something. So the flow is entering here and then swirling and traveling upward. So it kind of takes all the dust from inside and then goes up. So you can make use of these streamlines to see how the airflow actually is moving. So you can see here that the flow is actually a huge portion of the flow is getting pushed up. And and in that Venturi region you can see so many streamlines getting squeezed into this small neck or this small throttle area. And here you have so this building is causing some significant rising up of the downstream air. And so this looks cool, and you can get a lot of information from the streamlines plot, and also, like I said, from the velocity ratio plot. So the basic idea is to identify zones that are uncomfortable for pedestrian use. Like if the reason why I decided to choose this simulation or to try out the simulation is that when I was in Sweden during my master's education, I had this part-time job with food delivery, and I was using a bike, and on a windy day when I was biking, I experienced a really bad gust, and I was literally topped by the wind, and that was the first time that me being harassed by the wind. So, and that was in this Gamla area. So that's the reason why I choose this area and try to learn the simulation with this case study. So I think this is really good. You can get a lot of information from here. So I just applied the validated atmospheric boundary layer flow modeling from my previous simulation into this geometry, into the city block, and make use of it to study the plan of the city. So we had a lot of assumptions here. So I haven't considered thermal effects, I haven't considered the vegetation. So that's the next step. So in order to mitigate this cornering effects, as well as or reducing the effect of having gusts or having better pollution dispersion or protection. So by knowing the streamlines, we can actually manipulate the incoming flow with the help of some vegetation or wind barriers. So that's the next step. Making use of these results, we can do some planning. Okay, so I think you find this interesting as well, and you can try it out as a application of atmospheric boundary layer flow modeling and pedestrian wind comfort assessment. So thanks for watching.